and it's the comparison test and the limit comparison test. All right, the comparison test is sometimes called the direct comparison test because what we're going to do is we're going to compare series directly. And the idea is that if we have one that diverges, and we can show that the terms of another series are greater beyond some point, then it's got to diverge, right? Okay, good. And then the same thing if we have one that is convergent and all of the terms beyond some point are less, then that one has to converge also. Okay, good. So let's look at this. This will be something that'll be pretty easy to see. Now remember, no matter how easy something is to see, hand waving and logical leaps are not adequate, right? We have to have a complete argument. Okay, so we have the sum n equals 1 to infinity 1 over 2 to the n plus 1. Now, what I always do when I'm doing these problems to determine whether or not this series is convergent or divergent is I always start with some sort of a suspicion. Like, what do you suspect? What do you suspect about that thing?
As it approaches infinity.
Yeah, as n goes to infinity, what is it that you suspect about that thing? Do you think?
Approaching zero.
Well, the terms are certainly approaching zero, right? Like, if I was to try to start with the test for divergence, if I'm that sort of person that just likes to start that way, then I might look at the limit as n goes to infinity of 1 over 2 to the n plus 1. But, that doesn't require a logical leap to see that limit is 0, right? Because the denominator increases without bound. Okay, but what do I think about the terms of that series? Do I have a suspicion about whether or not that thing converges or diverges? Well, I tell you what, I kind of think that it converges. And so what I might do is think about, well, can I think of a series that I know converges that maybe I could compare to that one? What's that plus 1 in the denominator doing?
It's constantly making it smaller than.
Exactly. It's making the fraction itself smaller because it's increasing the value of the denominator, right? Okay, so here's what I'm wondering. I'm wondering about this one right here. Sum n equals 1 to infinity 1 over 2 to the n. In other words, what if I just eliminate that plus 1? Now, I know for sure that 1 over 2 to the n plus 1 is smaller than 1 over 2 to the n for all n, right? So I'm going to write that down. Remember, we have complete arguments. So for all n greater than or equal to 1, 1 over 2 to the n plus 1 is less than 1 over 2 to the n. Okay? So we've established something right there. We know that the one that we're working with in all of the terms are less than that one right there. Okay? Now, let's do this. Let's think if we can manipulate 1 over 2 to the n to look like something that we're familiar with. Now, if you remember last time, we goofed around with that exponent of n, right? So we might do something like this. I might do something like that. Because I could write 2 to the n as 2 times 2 to the n minus 1, right? Because what do I do when I multiply with like bases? Add exponents. And so there's a 1 and an n minus 1. That's going to add to n, right? Okay. Now, why is that handy? Well, let's keep going. I could write this as 2 fractions. And then Well, 1 raised to the n minus 1 is 1. So I could put that second fraction in parentheses with an exponent of n minus 1. So that's no problem. And not a logical leap. I mean, that's just an application of a property of exponents. Do we recognize that? What is that? Yeah, convergent geometric, right? Okay. So now I'm going to need to come up with some sort of an argument about this. But what is my argument? My argument's going to contain a lot of hand waving, isn't it? At this point, with what we have established up to this point, I can say, well, all those terms are smaller, and so therefore the sum is going to be less. But that doesn't say anything about a conclusion about convergence or divergence, right? I'm going to have to cite something that I know to be absolutely true. And so that thing that we are going to use is called the limit comparison test. So let's write down now what that is. So we got a good start on something that we suspect, but we need the tools that it takes to actually draw the conclusion, the sound conclusion, right? So here we go, the comparison test. The comparison test says, suppose that a series that has the terms a sub n and a series that has the terms b sub n are series with positive terms. Okay, so again, this is one of those conditions, right, that we have to remember. And again, I don't remember them, so I always make sure that I have some sort of a reference handy. Yes, sir?
Is this the direct comparison or the limit comparison?
Direct comparison.
Direct.
Yeah. Now, here then are the conclusions that we can draw from the comparison test. Okay, so if the sum b sub n is convergent and a sub n is less than or equal to b sub n for all n, then, and we kind of have just been talking about this, right? A sub n is also convergent. But we need this tool, the comparison test, so that we can cite it in our argument. Okay, now, and as you would suspect, if the b sub n series is divergent and a sub n is greater than or equal to b sub n for all n, then the a sub n series is also divergent. Okay, so in our work here, we have established, which part? Part 1 or part 2? Yeah, part 1, right? We have a series that we know is convergent. It's a convergent geometric series. And we've shown that all of the terms of our series are less. So now we can say, and really what we need to do though here to follow up on this, to complete this. Now, so far we have a very nice argument, don't we? I mean, there's not a lot of words in it, but there's no logical leaps. I mean, it's a good, solid, sound argument, top to bottom so far. But we do need to say something about this this series that we have compared to. So I'm going to say, the series 1 to infinity of 1/2 times 1/2 to the n minus 1 is a convergent geometric series. Therefore, sum n equals 1 to infinity, 1 over 2 to the n plus 1 is convergent by the comparison test. How does that feel? Yes, sir.
So you made a point of emphasizing that it's geometric. Does that have any relevance to the comparison test, or are you
No.
just including that?
Nope. Yeah, I just said it because I need to, I need to more than just say that this is a convergent series.
explain
I
why
need
it's
to,
convergent.
yes, exactly. Okay, good. Any questions? This is not bad, is it? Nah. Do they get worse? Yeah. Okay, let's see. I found one this morning that I thought was pretty good. That I think we should take a look at. So let's look at this one right here. Sum n equals 1 to infinity, n over n squared minus cosine square of n. I know, at first it looks like crap, man. Those n's are going to infinity. What in the world is going to happen here? But then I'm looking at it and I'm thinking, well, cosine. I mean, what do you know about cosine?
Cosine goes between 1 and 1.
Okay. Okay, yeah, exactly. Like if we were to draw a picture of the cosine function, I mean, we know that this thing, no matter what, never goes above 1 and never goes below -1. And if I square it, what happens?
The same thing, it never goes above 1, it never goes below -1.
Think about it again. If I square it, it never...
It's just 0 to 1.
Yeah, it doesn't even get negative, does it?
Oh.
Yeah, it goes between 0 and 1. And what am I doing? Yeah, so if I subtract something that's always positive in the denominator, what happens to the value of the fraction itself?
Always increase.
Yeah, it's going to get bigger, isn't it? Now, is it going to do that is that going to be really significant when we get out to infinity? Not really, but is it significant? Yeah, it's significant because it does make it less. Now, it doesn't make it significantly less out towards infinity, but that doesn't mean it's insignificant. It is significant because it is less. The fact that it is less. Okay, so here's what I think we need to do. I think we're going to be comparing, right? I think we need to think of something that might relate well, but just doesn't have that cosine square n in it. Like, for instance, what if I looked at the terms of n over n square without the cosine in it? Now, that would reduce, wouldn't it? To 1 over n? Hey, wait a second. How do n over n square minus cosine square n and n over n square compare?
N over n squared minus cosine n squared will always be greater than.
Yeah, greater than, always?
From all positive numbers from 1 to.
Think about it for a second, though. What does cosine range between?
0 and 1, so
The cosine square is 0 and 1, so it could be equal, couldn't it?
Could be,
Yeah.
Yeah, so it could be equal. So here we go. So we know that. So greater than or equal to, but that's significant, right? Because what's 1 over n?
Divergent.
Yeah, it's a divergent. Okay, so there we go. Now we got something going here. So here's what we know. Sum n equals 1 to infinity, 1 over n is we should say the, shouldn't we? It's got its own fame, is the divergent harmonic series. Now let's think about our argument. We have shown that the terms of our series are greater than or equal to the terms of a divergent series. That's solid. There's no leaps there. We haven't made any logical leaps here. So far we're in good shape with a good complete argument. I've discussed adequately the what we know about the divergent harmonic series. So now really all I need to do is apply the comparison test, right? So what I can do then is say, by the comparison test, sum n equals 1 to infinity n over n squared minus cosine square n is also divergent. Okay, any questions? It's not too bad. It looks bad to start with, but still not too bad. Let's look at another one. Let's look at this one here. So we have sum n equals 1 to infinity e to the minus n over n plus cosine square n. Okay, so now I'm adding something in the denominator, but boy, that e to the minus n sure is.
Put that on the bottom.
Well, maybe that might be something eventually, but I don't know anything about that at this point. If I'm gonna put it on the bottom, well, I'm probably not gonna want two terms in the bottom. I'm probably gonna want something closer to something I know something about, right? Okay. Well, we got to have some sort of a suspicion. I mean, like you said, the thing will go to the bottom because it's got a negative exponent, right? And then what happens? Everything ends up on the bottom, doesn't it? And n's just going to get bigger. And then e to the n's going to get bigger, and n's going to get bigger. Cosine square n doesn't do a whole lot. But what do you suspect then about this thing?
It's gonna go to 0.
Looks like it, doesn't it? Okay, but we still, if we're going to use a comparison test, I mean, I have to compare this thing to something that I know converges, if I think it converges, and I have to, do some algebra to show that it does.
Okay, if we can prove that this is greater than 1 over n, because it's in a similar form because it's 1 over...
Think about 1 over n.
terms.
What do you know about 1 over n?
It's divergent.
It's divergent, and what are we suspecting?
It's convergent.
Yeah, good. But that's good, Everett. That's the sort of way that we want to think. Okay? I don't know. Take your pencil, scratch a little bit. See what you can come up with. See if you can come up with some sort of a plan. Any kind of an idea for how this thing works. So, like I said, if we remove the cosine square, don't we have this relationship?
Yeah. So if we can get the second equation to be a geometric series.
Yeah, I don't think you're going to. Yes, sir.
Can we if we compare something, can we compare what we're comparing it to another thing?
That's what we want to do. Yeah, that's good. So you're saying, like we've compared these two, But what if we compare it to something else like that?
I wasn't thinking that exactly, but.
Is that true?
For all values of n, yes,
Why?
because we're always one or greater, and
Exactly. That denominator is bigger, right? That makes the fraction smaller. So that is definitely a less than relationship there. I think we have a much better shot at figuring out what happens with e to the minus n than we do with e to the minus n over n. Okay. What are the tests that you have so far? You have the integral test, don't you? Will you please tell me what are the conditions and the conclusions of the integral test, please?
If f is continuous, positive, and decreasing function on 1 to infinity, then the series is convergent if and only if the improper interval is convergent.
So they either both converge or they both diverge, right? Now what are we working with here? We're working with something that we think converges, right? So if I can show that e to the minus n converges, and this one is less than that,
it has to converge.
right? So what are we talking about here? We're talking about maybe using the integral test to see if e to the minus n converges. So give that a whack. See what happens. Is that what you guys got? Okay, but wait. Okay, I know what the integral test says. But
How do you kind of transition that logic into the two other?
well, yeah, we have. I mean, like I know that I have to decide. Well, do you remember with the improper integrals? How was it that we decided if an improper integral converged or diverged?
If it approached a value.
If it just approached a value, right? Yeah, very good. Which it does, right? Okay, so how do we finish talking about this then? So, I think what I would say is, since the improper integral integral 1 to infinity e to the minus x dx converges, the series sum n equals 1 to infinity e to the minus n converges by the integral test. Okay, so our argument's going along pretty good so far. Okay, I've got e to the minus n converging, but I have a really nice string of inequalities there, showing that our series is less than that one in all the terms, right? So then we can say, therefore, by the comparison test, sum n equals 1 to infinity e to the minus n over n plus cosine square n also converges. Okay? Any questions? Okay. I have diverged from my originally planned notes a little bit, but that's all right, because that stuff was good. All right, so let's look at something else. Let's determine whether sum n equals 1 to infinity 5 over, oh, that's a long fraction bar I made. Wonder why. 2n squared plus 4n plus 3e raised to the I pi integral x squared dx. Kidding about all that part. Let's just make it a 3. Converges or diverges? What's your suspicion?
I think it converges.
You think it converges? Yeah, and I think it's good to start off with a suspicion like that. Why do you think it converges?
Bottoms. Going to
Yeah, the bottom's getting huge, isn't it? And the top isn't doing anything. Yeah, so I think something's going on there. So I'm the same. So keep going.
So why can't we just say that it converges because the bottom is going to 0? That's what I was, because the bottom's going to infinity.
Yeah.
Therefore.
Okay, yeah, that's a good question. So what you're doing there is you're trying to apply a test for convergence based on the value of the last term, right?
Correct.
But what was it that the value of the last term told us?
It's not always. If it's 0, it doesn't mean it's always convergent.
That's right. But if it's not 0,
Then it can never be.
then it diverges.
Gotcha. Okay.
Okay, but that was a really good question
That's
because
what I was missing. I forgot.
that is the very thing that we want to get straight in our heads, right? Because those leaps of logic are, boy, it seems logical, right? But it isn't.
So my first instinct is not to bother with all that, but say that this is always going to be less than, we'll say like 1 over n to the 5th.
Could we use like the
And then 1 over n
rate of
to the
change
1
stuff
over n.
that we did like
We just gotta go
earlier
test
on?
this.
Where it's like,
To see if it's decreasing?
or no, I just mean like define the functions like
value
compared to like the bottom part of like 2 and squared plus 1 plus 3.
I don't think I would even go that far. I'd keep it simpler. I'd try to keep it way more simpler than that.
Professor, can I test something that I've got just to ask? See if
Sure.
So theoretically, that will always be less than a fraction, say, oh wait, never mind.
Well, let me say this.
It won't be less than this one.
That'll always be less than something than if I just take out that 4n plus 3, right?
Yeah.
So I think I might start there. I think I might start by taking out that 4n plus 3. And when you do that, what are you left with? What kind of a series? Jason, this is your favorite kind of series. What is it?
P series?
Yeah, a p-series with,
P greater than
1.
so it is convergent, right? Very good. So I think that's what I would say. I would say this is a convergent p-series with p equal to 2 greater than 1. Yes, sir.
So I wanted to go down the route of the integral test. Would that still have applied in this case?
Ah, man, why?
Because I like integrating.
I did the most convoluted way and then I did
Yeah.
the 2 next.
I would try not to establish that habit. I would try to establish the habit of looking for the simplest route there. Always. Yes, that's exactly right. Is the patterns that are going to get you that path of least resistance. Okay.
So when I've got the test of 50 questions, I have to find the patterns of all of them.
Well, you'll do so much practice, you'll see them. And if not, you'll fail. Okay, so here we go. But I still need a complete argument, right? So I've established that this is a convergent p-series. I've established that the terms of the series that I'm working with are less than the terms of this convergent p-series. So what would I say now?
Therefore, by the comparison test, the sum of n equals 1 to infinity is of 5 over 2n squared plus 4n plus 3 converges.
No? I'm just kidding. Yeah, that's right.
Okay.
5 over 2n squared plus 4n plus 3 converges. Good job. So test for convergence or divergence. Sum k equals 1 to infinity, natural log of k over k. So what's going on here with those terms?
It's indeterminate right now.
Yeah, it's infinity over infinity, isn't it? Yeah. What the heck?
Is all Pitel's rule?
I was gonna ask this thing.
No. But let's not within the series itself, but maybe later on, like when you're doing part of a comparison test or something like that. Another test that gets you there. But let's think about this for a second.
Compare it to the natural log of k, because as k gets bigger.
No.
wouldn't it-
The bottom's getting bigger quicker than the top, isn't it?
So then-
But what do you but remember what we did? We started with a suspicion. What is your suspicion?
It's different.
That it's what?
Divergent.
You think it's divergent?
Convergent.
Yeah, I do
think
too.
so. Oh,
I think it's divergent. Yeah.
Yeah.
There's nothing
It's-
that would tell us it could converge so far.
Yeah, I think what we probably then maybe might want to do is compare it to something that's divergent, right? Okay, so no, not or. So can you think of something that is divergent that would be it would be convenient to use?
1 over k.
1 over k is a divergent harmonic series, right? So let's think about this for a second. What about natural log of k over k? How does that compare to 1 over k?
If we put q to natural log of k, then if we differentiate it, we are going to get du is equal to 1 over x dx, which would,
You're working too hard.
So the natural
So-
log of k over k would be greater than or equal to 1 over k.
Well, when is the natural log of k 1?
0.
When k is
0. Yeah.
no, you can't be 0.
Oh, E?
Well, when k is e, right? Okay, so here's what I could say. I could say that the natural log of k, we did this the other day, didn't we? The natural log of k over k is bigger than 1 over k for all k greater than or equal to 3. Jason, I mean, like, I want you to, like, you know, investigate all those things you're talking about, but don't work too hard, okay? Try to get it down into the simplest terms that you can, because you don't have time to do that much stuff, okay? Better to look for things that occur over and over. And that's really what this is about. And I'll tell you this too. What we're headed towards is actually approximating functions with series. Approximating the values of functions with series. And that will be all about recognizing patterns. So that's what we're doing, is we're kind of preparing ourselves and building all this up, recognizing patterns. Okay, here's what we know. We know that sum 1 over k is the divergent harmonic series. Therefore, by the comparison test, sum k equals 1 to infinity natural log k over k is divergent. Okay, remember I'm having to edit all this out. Limit comparison test. The limit comparison test. Suppose the sum a sub n and sum b sub n are series with positive terms. If the limit as n goes to infinity of the quotient of these terms is equal to some finite number, c, where c is a finite number and c is positive, then, and so here's going to be the conclusion that we draw with the limit comparison test. That is going to be either both series converge or both series diverge. So that's going to be super handy. Okay, so let's look at this. Let's look at the sum n equals 1 to infinity 1 over 2 to the n minus 1. Okay, what do you suspect? You think it converges?
Because like
Yeah.
as n goes to infinity, the bottom's gonna be like huge.
And it's never indeterminate because the bottom will never be 0 because you're starting at
Oh,
1.
actually, wait, no, add.
Well, what kind of a series are you thinking about? Maybe would be comparable. Not a p series because it's not a constant exponent.
1 over 2 to the n.
Well, that would be geometric. That converges, right? But how does this one compare to 1 over 2 to the n? Is it bigger or smaller?
Greater.
It's bigger. Okay, wait. 1 over 2 to the n is convergent, so a direct comparison won't work. So maybe a limit comparison would work. Maybe that would work. Now, is everybody seeing the logic here? So, yeah, you're right. It was good to think about 1 over 2 to the n. That's geometric. It's similar, and it would apply the similar technique that we used before, just dropping the end off, right? But the problem is that that's bigger. So we can't use our direct comparison test. Okay, so, but maybe we can use 1 over 2 to the n. So let's do this. Let's let a sub n be our series here, the terms of our series, 1 over 2 to the n minus 1, and b sub n be 1 over 2 to the n. We know that the series, I might even write this up here. The series n equals 1 to infinity of 1 over 2 to the n, and we did this earlier, didn't we? We can write that as 1/2 times 1/2 raised to the n minus 1, which is a convergent geometric series.
For a complete argument, we would have to show that 1 over 2 to the n is a geometric series in order to prove its convergence.
Yeah, I mean, like right now I might hand wave because we already did this earlier today. But no, when I'm making my argument, I need to show that this is a convergent divergent geometric series. Okay, so now we already decided that we can't use a direct comparison test between these two. So maybe the limit comparison test. So we're going to go the limit as n goes to infinity of a sub n over b sub n, which will be the limit as n goes to infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. Now, I'm going to invert and multiply, so that'll become the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Now, well, what's the top and what's the bottom going to be in the limit? What did you do in Calc 1 for those?
Can you use old L'Hopital's rule here? Because it is a limit.
Well, I don't even think you need to do that because, I mean, remember what you did in Calc 1? Like one of the very first things you did with a limit was you would divide the top and bottom by whatever has the biggest degree in the denominator, right? So in other words, I'd multiply the top and bottom by 1 over 2 to the n. I can do that. So what I'd have is the limit as n goes to infinity. Everett, again, we're looking at keeping this thing as simple as we can. And here what we wind up is 1 minus 1 over 2 to the n. And what's the limit of 1 over 2 to the n? That's 0, right? That last term is 0. So what's this limit? Yeah, this limit is just 1.
And then L'Hopital's rule would have been difficult with the next one.
It just would have been longer and messed up. And by the way, how do I find the derivative of 2 to the n?
That's ln.
Yeah, exactly.
Which is
Yeah, I've got logs involved, so I'm not even going to bother with that. Okay. This is bigger than 0. That's the point, right? Because that's what the limit comparison test tells me, that if this is a constant that is greater than 0, which it is, then the conclusion is that either both series converge or both diverge. We already established that one of them is a convergent geometric series. So now all I really need to do is just say, therefore, by the limit comparison test, sum n equals 1 to infinity 1 over 2 to the n minus 1 converges. Any questions? Okay, so let's do this. I would like for you guys to mess with this for a little bit. So the sum n equals 1 to infinity of 2n squared plus 3n over the square root of 5 plus n to the 5th. What? Again, you want to start with a suspicion, right? Because that's how you're going to determine what series you might compare that to. I mean, if I was me, this is how I'd start.
So how do you justify getting rid of the 3n there, Professor? It's just not impactful enough to...
I'm not doing a direct comparison. I'm just coming up with something that I think would sit well in a quotient that I can pretty easily figure something about.
Okay.
Does that make sense?
Sure. That's what you'd like to believe. have a lot more freedom with the limit comparison test than with almost every other test.
Yeah, sort of, except, I guess what you're doing is, first of all, so as far as the freedom goes, well, yes, but I'm starting with a suspicion. Because what is 2n squared over n to the 5 halves? What is that?
2 over squared.
What's that?
Convergence. It's convergent because the bottom goes.
What is it, Jason? 2
It's a
over
P
n to the
series.
1 half.
Yeah.
It's a P series that's divergent because it's less
The
than
divergent P series. Very good, very good.
Yeah.
Okay, so it must be that I'm assuming that guy diverges if I'm going to try to do a limit comparison test with a divergent series.
I knew it diverged secretly.
Is that making sense to everybody? So do some algebra. What did we do last time? We used that thing that we used like when you first started doing limits in Calc 1.
Yeah, you just sort of divided by.
Yeah, divide by the whatever you need to that has the biggest biggest exponent in the denominator. Okay, well I've got a square root of 5 plus n to the 5th, but if I multiplied the top and bottom by 1 over 5 and 1 over n to the 5 halves, couldn't I pass it underneath that square root? I could, couldn't I? So in other words, I'm thinking about doing this. Multiply the top and bottom by 1 over n to the 5 halves. That's just the square root of n to the 5th, right? 1 over the square root of n to the 5th. So I have the limit as n goes to infinity. Now, the convenient thing, of course, that happens on the top is that I wind up with 2 plus 3 over n, right? And now in the bottom, so here's the interesting part. So that n to the 5 halves is the square root of n to the 5th, and it's in the denominator. So I'm going to wind up with the square root of 5 over n to the 5th plus, well, n to the 5th over n to the 5th, right?
Now can we just start saying what goes to 0 and what cancels out? Finish, be done.
Well, yeah, I'm probably going to rewrite this a little bit, though. I'm going to go 2 plus 3 over n over 2 times the square root of 5 over n to the 5th plus 1, right? Because it's that plus 1 that's significant here, right? Because so the 3 over n and the 5 over n to the 5th, those are going to 0. Yes, that's correct. So what do I wind up with in the top? I wind up with 2 in the top. I wind up with 2 times 1 in the bottom, right? 2 times the square root of 1. So this turns out to be 1. Now, what is the significance of that?
They both diverge.
Yeah, this limit comparison test says just that if it's equal to some constant value that's bigger than 0, then I either have a situation where both series converge or both series diverge. I know exactly what's going on here, right? I know that 2 over n to the 1/2 diverges. Oh, but wait, I have not established that yet, have I? All I've done is said that I'm going to let b sub n be equal to that, but I haven't said why I'm going to let it be equal to that, or what is the significance of that at all. So I'm going to need to establish that. So I'm going to have to say, all right, sum n equals 1 to infinity 2n squared over n to the 5 halves is equal to sum n equals 1 to infinity 2 over n to the 1/2, which is a divergent series. Okay, great. Yes, sir. Now, go ahead.
Could you just skip the 2n squared over n to the 5 halves?
If you want. Okay, so now we can state our conclusion, right? We can say, therefore, by the limit comparison test, sum n equals 1 to infinity 2n squared plus 3n over the square root of 5 plus n to the 5th diverges.